All right. Moving onwards and upwards. Let's see. It's just these ads. I don't want to see any breasts. That's the issue with these ads. All right, we're going to reader view here. Not too many wonderful pictures. All right. NASA selects a wild plan to, quote, swarm Proxima Centauri with thousands of tiny probes. Humans have dreamed about traveling to other star systems and setting foot on alien worlds for generations. To put it mildly, interstellar exploration is a very daunting task. As universe today explored in a previous post, it would take between 19,000 and 81,000 years for a spacecraft to reach Proxima Centauri using conventional propulsion. Now, Proxima Centauri is the closest star system to us that has a planet within the habitable zone. So it orbits within the zone that is just the right temperature, that it's not too hot, that it's not too cold. So very interesting from there. But it's what, three, maybe 4 light years away? Yeah, I think it's like four something light years away. On top of that, there are numerous risks when traveling through the interstellar medium, not of all of which are well understood, because there might be some things in your way. Under the circumstances, gram scale spacecraft that rely on directed energy propulsion, also known as lasers, appear to be the only viable option for reaching neighboring stars in this century. So, taking basically very, very small spacecraft that are less than a pound, less than a half a pound, like very, very extremely light, and using lasers to shoot at them and then propel them up to incredibly fast speeds, faster than what a rocket engine could do. Because rocket engines, they might produce a lot of thrust, but they also weigh a lot and they take a whole lot of energy to actually move. Proposed concepts include the Swarming Proxima Centauri, a collaborative effort between space initiatives and the Initiative for Interstellar Studies, led by Space Initiative's chief scientist Marshall Eubanks. The concept was recently selected for Phase 1 development as part of this year's NASA Innovative Advanced Concepts program. Let's see, right here. This is basically the plans right here. But let's go back and continue reading. According to Eubanks, traveling through interstellar space is a question of distance, energy, and speed. At a distance of 4.25 light years, so I was close, 40 trillion kilometers or 25 trillion miles from the solar system, even Proxima Centauri is unfathomably far away. Yeah, that is pretty far. That's not, I mean, I think to Mars, I want to say it's about 100 million miles from here, I think. To put it into perspective, the record for the farthest distance ever traveled by a spacecraft goes to the Voyager 1 space probe, which is currently more than 24 billion kilometers. I want to say billion with a B. The previous number, we're in the trillion, so we're with a T. So still got quite a ways to go. Using conventional methods, the probe accomplished a maximum speed of 61,500 kilometers per hour or 38,215 miles per hour and has been traveling for more than 46 years straight. So it's gotten about 15 billion miles in under 50 years. And Proxima Centauri is 25 trillion miles. So, it's got a long ways to go. In short, traveling at anything less than relativistic speed, a fraction of the speed of light, will make interstellar transits incredibly long and entirely impractical. All right. Let's look up speed of light miles per. All right, miles per hour. All right, so this is the speed of light right here. 670,600 Oh, 670,616,629 miles per hour. That's the speed of light. So 186 miles a second. That's pretty fast. And unfortunately, we don't have anything that can really come close to that. Um, Given the energy requirements, this calls for anything other than small spacecraft with a maximum mass of a few grams is feasible. As Eubanks told University Today, quote, of course, rockets are a common way to go fast. Rockets work by throwing stuff out the back. The momentum in the stuff going backwards, equaling that in the velocity, increases the vehicle in the forward direction. The essence of rocketry is that it is only really efficient if the velocity of the stuff going backwards is comparable to the velocity you want to gain going forward. If it isn't, if it is very much smaller, you just can't carry enough stuff to gain the velocity you want. The trouble is that we have no technology, no energy source that would enable us to throw out a lot of stuff at anything like 60,000 kilometers a second. And so rockets won't work. Antimatter might conceivably enable this, but we just don't understand antimatter well enough and can't make anywhere near enough of it to make this a solution probably for many decades to come. So maybe antimatter is the answer. Maybe that's what these other alien civilizations and who have I mean, there's always videos of there's a guy I follow for a quick tangent. Guy I follow, Jeremy Corbell. He's been on Joe Rogan a couple of times. He's a big UFO guy. He went to Congress when they were having the hearings on the UFO programs. He's been posting a bunch of videos about this new UFO spacecraft with videos and stuff. It's very interesting. It's very interesting. Now, are those civilizations able to travel here from, say, 20 to 50 light years away, which is not very far in the grand scheme of even the Milky Way galaxy? I mean, we're talking hundreds, if not maybe a couple million light years away is the potential that people could travel here to us. So 10 to 25 light years is pretty much nothing. Let's say they have antimatter technology. Let's say they're maybe 500 to 1,000 years more advanced than us, which is not, in all relativity, not that much time difference either. Why not would they come here? They can travel here using their antimatter engines and put along. All right, let's continue on. In contrast, concepts like Breakthrough Starshot and the Proxima Swarm consist of inverting the rocket, i.e., instead of throwing stuff out, stuff is thrown at the spacecraft. Instead of heavy propellant, what constitutes the majority of conventional rockets, the energy source for a light sail is photons, which have no mass and move at the speed of light. Is that photons? Maybe? I don't know. But as Eubanks indicated, this does not overcome the issue of energy, making it even more important that the spacecraft be as small as possible. Bouncing photons off of a laser sail thus solves a speed of stuff problem. But the trouble is there is not much momentum in a photon, so we need a lot of them. And given the power we are likely to have available, even a couple of decades from now, the thrust will be weak. So the mass of the probes needs to be very small, grams, not tons. This proposal calls for 100 gigawatt laser beaming, boosting thousands of gram scale space probes with laser sails to relativistic speeds, 10 to 20% the speed of light, which is incredibly fast. I mean, the Voyager probe got to like 100th, 1,000th of the speed of light. So these things would be going insanely fast, but they got to travel a far distance. They also proposed a series of terrestrial light buckets measuring a square kilometer in diameter to catch the signals from the probes once they are well on their way to reaching Proxima Centauri. By their estimate, this mission concept could be ready for development around the mid-century mark and could reach Proxima Centauri and its Earth-like exoplanet by the third quarter of this century, 2075 or after. So hopefully in my lifetime. I'll be pretty old by 2075, but I'll be in my 70s, close to 80. Damn, right? I don't know. 1998. Who knows? Who knows? 77? I think so. In a previous paper, Eubanks and his colleagues, and like I said earlier, this is kind of the idea for it. So you see the swarm right here. Let me zoom in. These are all the little probes right here. This is Proxima B. Proxima Centauri is the actual star of it, but this little planet is Proxima B that's in the habitable zone. So we send these swarm of these very, very small devices. They hit pretty much coming from the northwest down onwards to it, and then they kind of just orbit around this and probably take pictures and get readings and maybe find people. All right, let's continue on. By raising the collecting data to a doable 1 kilometer squared and having many probes coordinate their sending, we can get a reasonable, if smaller, bit rate. However, the 8-year round trip lag on communications imposed by interstellar distance and general relativity makes controlling the probes remotely from Earth impossible. As such, the swarm must possess an extraordinary degree of autonomy when it comes to navigation. Yeah, coordinating 1,000 probes. So it's not like it's just one probe that has to worry about itself. There's a lot. And deciding what data is returned to Earth. While these strategies address distance, energy, and speed, at least for the time being, there is still the issue of how much it will cost to create the swarm and the associated infrastructure. I mean, you got to get a freaking laser. So I can imagine it'd be pretty expensive. And then, yeah, here it is. The single greatest expense will be the laser array itself, whereas the gram scale craft will be reasonably cheap to produce. As Eubanks told University Today in a previous article, their proposal can be developed within a budget of $100 billion. Oh, cheap, cheap. But as Eubanks emphasized then and now, the benefits of the mission architecture they've envisioned are legion, and the payoff of sending a swarm of probes to Proxima Centauri would be astronomical. I mean, that would be insane. Insane if we're able to do that, at least in my lifetime. The simple fact is that the cost of a laser-propelled interstellar mission with lightweight probes and a huge laser system to propel them to stars will be dominated by capital cost, the cost of the laser system. The probes themselves will be pretty cheap by comparison. So if you can send one, you should send lots. Clearly, sending a lot of probes brings the advantage of redundancy. Space travel is risky, and interstellar travel is likely to be especially risky. So if we send a lot of probes, we can tolerate a high loss rate. Exactly. You just need basically one to make it. But we can do a lot more. We want to look for signs of biology and even technology, and so it would be good to get probes very close to the planet to get good pictures and spectra of the surface and atmosphere. That will be tough for one probe as we don't know very well where the planet will be 24 plus years in the future. By sending a bunch of probes in a spread, at least a few could get us close to the planet, giving us the close-up view we want. Beyond that, Eubanks and his colleagues hope that the development of a coherent swarm of robotic probes will have applications closer to home. Swarm robotics is a hot field of research today and is being investigated as a possible means of exploring Europa's interior ocean, digging underground cities on Mars, assembling large structures in space, and providing extreme weather tracking from Earth's orbit. Beyond space exploration and Earth observation, swarm robotics also has applications in medicine, additive manufacturing, environmental studies, global positioning and navigation, search and rescue, and more. While it could take many decades before an interstellar mission is ready to travel to Alpha Centauri, Eubanks and his colleagues are honored and excited to be among NASA's selectees for the 2024 NIAC program. Huh. So this is their paper that they did a couple of years ago. You can see, when does it say that this was written? Does it say? Um, Interesting. Now look at that. Figure 1. Artist's impression of swarm passing by Proxima Centauri and Proxima b. The swarm's extent is 10 about 10 larger than the planets. Yet the 500 kilometers spacing is such that one or more probes will come close to or even impact the planet. Wow. Should be possible to do transmission spectroscopy with such swarms. Very cool. Yeah, and I'll put this below. This is really cool to read. This is actually not a super in-depth study where it's impossible to understand this. I mean, some of the stuff is just a little a little crazy, but you can kind of see here. These are the actual swarmers themselves, and you can see these sensors that will get the light. You got a little bit of math here, time and velocity on target, um, chips and all this kind of stuff, swarming and discovery sweep, all this kind of stuff that you can see right here. Very, very cool stuff, and it's yeah, you can see where Centauri is right here based on the other things in the galaxy. So very cool stuff right here. Here's where all this stuff right here. Very cool, very cool. All right. Yeah, very cool. All right. Boom. And then the last thing about here is, let's say, let me stop the share for a second. Let's say let's say it takes, because the other thing, and I talked about this with the OSIRIS-REx mission, where they were tens of millions of miles away from us here on Earth. I think they got it to 200 million miles away at one point, where the probe was actually on the other side of the sun. One of the issues that you run into is communication to the actual probe. So obviously, you can't send a message to the probe faster than the speed of light. So that's kind of the speed limit at what you can send your radio signals and your communications and what you can get the data from. It's not like you're playing with a Xbox controller and it's instantly being inputted into that probe. No, you have to either have the probe make its own decisions, and with the help of AI, maybe one day we'll have probes that are fully autonomous. A couple probes that are on Mars already are pretty autonomous themselves. There was one, I don't know why I can't think of the name right now. I should know what it is because I saw the actual landing. Perseverance? I don't know. But there was one that landed on Mars, and the descent and the deployment of the chute and all that stuff was done by the actual spacecraft. So it saw what the conditions were as it was coming down to the surface. It was like, I'm going a little bit too far to the left. Let me adjust. Let me do this so that I can go down straight. Okay, we're at this whatever altitude. Let me deploy my chute. So we do have examples of this happening. And then obviously with the OSIRIS-REx mission, same thing happened there, where that entire descent of the aircraft was done by itself, where it had to make the decision of how close it would actually get to the surface. And we saw that video that I showed of it getting to the surface and pushing that collection basket, if you will, down to the bottom, hitting it, pressing out that gas, I think it was nitrogen gas, and then collecting its samples. Very, very cool stuff. And now imagine that happening to these little tiny devices that we're going to be sending to Proxima Centauri. And they're saying it could get there in about 8 years. But it's got to be traveling so fast that it doesn't even make sense. 10 to 20% the speed of light is incredibly fast. I mean, all right, let's just do miles per hour. All right, 10% of this is 67 million miles an hour. Still insanely fast. They incomprehensible fast. But it does seem possible. I mean, in theory, this is something that is possible. And if we are able to get to a point in our technology and in our society where we actually want to do this, where we want to go visit this other planet, we want to go visit another solar system, we could. And I think that the prospect of that extre is extremely exciting. So let's take a look at what we would potentially be visiting. Let's go back. All right, planet Proxima Centauri, right here. That's what the planet looks like. Let's compare it to Earth. Basically, same size as Earth. Very cool. Now let's look at the system right here. You see, this is the habitable zone right here. Boom, turn it off, turn it on. Very, very cool. And then compare it to our solar system. Very, very small. You see Earth all the way out there compared to Proxima Centauri, where it's right here. Very, very small. Now compare this star. I mean, look at it. It's a M-type star, the most common type of star, which is much redder, cooler, and dimmer than the sun. Now, what does it look like compared to the sun? Much, much smaller. Very, very cool. Like I said earlier, the orbital period, all of this stuff is good to know. Here's all the stuff. Potential rocky world. You can see the planet comparison, sun comparison. And then here's that thing. How long would it take to travel? All this stuff. There's light speed. That's Voyager, 75,000 years. 600 miles an hour would take 5 million years. 120 miles an hour would take 24 million years. Oh man, so it's pretty far away. It's pretty far away. All right.